All right, Wildcats, here we are on the third day of note-taking, page 32, chapter 1, lesson 3. Looking at our notes, we basically have a full page, so we're going to go ahead and flip it over to the back. You can still see the fold down the middle. We're going to need our red pen or red colored pencil, or write it in a pencil and then underline it with like a red crayon or something. Map scale. Capital M-A-P, scale, capital S-C-A-L-E. Switch to our pencil. Remember that a map is a model of the actual world. For a map to be meaningful and easy to use, it must include a scale. A map scale is a ratio that relates a distance on the map to the actual distance on the surface of Earth. Okay, so map model, map, M-A-P, equals model, M-O-D-E-L, of, O-F, actual, A-C-T-U-A-L, world, W-O-R-L-D. Scale is a ratio, relates distances. Scale, S-C-A-L-E, equals ratio, R-A-T-I-O, relating, R-E-L-A-T-I-N-G, distances, D-I-S-T-A-N-C-E-S. So I know in math you're learning about ratios like unit rates, miles per hour, or gallons per second. A scale is going to be a similar ratio relating distances. For the map below, the scale is 1 to 300,000. This means that 1 centimeter on the map represents 300,000 centimeters, or 3 kilometers, on the ground. To find the distance between two places on a map, use a ruler to measure the distance in centimeters. On this map, for example, the distance between the Los Angeles International Airport and Van Nuys Airport is about 12 centimeters. To find the actual distance, multiplying this value by 3 kilometers per centimeter, so the actual distance is 36 kilometers, which is about 22 miles. Every map has a unique scale. Read the scale carefully to estimate the distance. Okay, so 1 to 300,000. How do we know that? The scale is down here. So it shows you that on the map, this tiny little distance right here is 1 kilometer. So, for example, if I go from that little dot to the intersection of Lincoln and Venice Boulevards, that looks like it's about 2 of those, or 2 kilometers, a little more than a mile. Okay. Los Angeles International Airport. Where is that on here? Look for LAX or Los Angeles International Airport. There it is, down here. LA International Airport, right down here. Van Nuys Airport. Okay, so I'm looking for Van Nuys. Westmont, Florence, Maywood, Bell Gardens. Where in the world is Van Nuys? Glendale, Burbank. Oh, I just saw it. Van Nuys Airport, way up there. Okay, so LA Airport is all the way down here. And Van Nuys Airport is all the way up there. Okay, when they say they measure it to be 12 centimeters. So if they got out a ruler and measured from here all the way to there, it's 12 centimeters on this piece of paper. Okay, now if you take the ratio and you expand it, that distance is actually 36 kilometers. And let's see if that makes sense. Okay, that 6 kilometers is about 2 fingers. So I ought to be able to do that 6 times, or 6 times 6 equals 36. Right? 1, 2, 3, I'm about halfway, 4, 5, 6. Sure enough, that's about 6 of those. 6 times 6 is 36, so it's about 36 kilometers. Okay, so that's how you can do it. Now, on a phone, you pinch or you spread to zoom in and out. The scale changes every time you pinch and every time you spread. So the scale is always changing on a phone or a tablet or something like that. Okay, we don't need to use any of these specific numbers for our notes, but we just need to understand how a small distance on a piece of paper can actually be a big distance in real life. A map scale is used to find the actual distance between places. Approximately how far is it from Pasadena to Encino? Okay, I know that Pasadena is over here, and then Encino, where is that? I'm looking down here at the bottom. Encino, I'm looking for black words because those are the city names, I think. Southgate, Downey, Bell Gardens, East LA, Monterey Park, Rosemead, Alhambra, San Gabriel, Pasadena, Altadena, Glendale, Burbank. Huh, I'm having a hard time finding Encino. Where is it? Okay, I finally found Encino. It is this tiny little thing right over here. Okay, so going from Pasadena to Encino, I'm going to do that two-finger thing again. 1, 2, 3, 4, and a little bit more. So 6, 12, 18, 24, and some more. I'm going to say around 3 or 4. So it's probably right around 27 kilometers to get from Pasadena to Encino. All right, let's do the next one. Geologic maps. Red pen. Geologic. We're going to skip a line to leave some space in case we have to come back and add anything. Capital G-E-O, Geo, logic, L-O-G-I-C. Maps. Capital M-A-P-S. Okay, back to our pencil. Some maps show very specific kinds of information. One such map is a geologic map. A geologic map usually shows types and distributions of surface rocks. It may also show other surface features such as rivers and lakes. Okay, so types and distributions of surface rocks. Types, T-Y-P-E-S / distribution, D-I-S, T-R-I-B-U-T-I-O-N. Types / distribution, surface, S-U-R-F-A-C-E, rock, R-O-C-K. It may also show other surface features. Other, O-T-H-E-R, features, F-E-A-T-U-R-E-S, / landforms, L-A-N-D-F-O-R-M-S. Scientists often study geologic maps to learn about the different types of rock in an area. This can help them find resources such as minerals, ores, groundwater, coal, or petroleum. Okay, so minerals would be like metals, ores also like metals, groundwater, a valuable resource as we learned a little bit earlier, coal for burning and power, and petroleum for oil or gasoline. They also use geologic maps to identify areas where dangerous events such as landslides, sinkholes, earthquakes, or volcanic eruptions may happen. Okay, so geologic maps kind of have two things. Resources, R-E-S-O-U-R-C-E-S, resources. And then they can also show dangerous events. So I'm going to call those hazards. Resources and down, 3 down, hazards, H-A-Z-A-R-D-S. Engineers and builders use geologic maps. By studying the composition of the ground, they can design and safely construct buildings, roads, and bridges. Okay, so they have to know what the ground is made of that they can build there. For example, in Louisiana, near New Orleans, the ground is very soft and muddy and wet. They have a hard time building buildings because the ground is not stable. So they have to do special things and engineer their buildings in order to get them to be sturdy. So I'm going to say something to that effect. Engineers, E-N-G-I-N-E-E-R-S. Engineers study, S-T-U-D-Y, arrow. And then let's do construct safely, C-O-N-S-T-R-U-C-T, construct. I'm running out of space, so I'm just going to go underneath. Safely, S-A-F-E-L-Y. Okay, so map scale. A map is a model of the actual world, and the scale is the ratio that relates distances. So we know that a small distance on the paper can be a large distance in real life. Geologic maps show the types and distribution of surface rocks. It also has other features and landforms like rivers or mountains. It shows resources that we can use, and it also shows hazards like ground conditions or volcanoes or things like that. The engineers can study a geologic map so that they construct things safely. Okay, here's an example of a geologic map. Here are the examples of the types and distributions of surface rocks. Cenozoic, sedimentary rocks. So Cenozoic and Mesozoic are like eras of the Earth's history in terms of billions of years. All the yellow stuff is sedimentary, and we're going to learn what that means later, but basically that's kind of like looser dirt that's on top of the bedrock. The red, Cenozoic volcanic rocks. So up here, there used to be volcanoes, millions or billions of years ago, and that has hardened. Mesozoic, sedimentary rocks in green. Okay, so that's all the stuff here on top, and that might give us clues whether or not the Mesozoic era was sooner or later. Intrusive igneous rocks. Okay, that's basically things like granite. That's magma that used to be underground and has hardened into solid rock. So you can see that San Francisco is built on this purple stuff, igneous rock. Well, that is hard, solid rock. So even though there's a lot of earthquakes all up and down the coast of California, San Francisco is built on bedrock, so the buildings are going to be pretty sturdy. Landforms and features like mountains. You can see some of the contour lines that we talked about before. You can see major cities, names of valleys, rivers, and large bodies of water. So all those things we talked about are in the geologic map. Now this particular map doesn't really have resources other than water and rivers or what types of rocks are here. But sometimes you might see a picture of like a little bin of coal, or you might see like a little drop of oil for oil. On this geologic map of the San Francisco Bay Area, colors show the different types of surface rocks. Notice the contour lines are included to show the topography. Okay, so we have the colors showing the types of rocks that we just talked about, and we have the contour lines showing topography, which we learned about previously. Why is a map's scale important? Okay, let's look at our notes and see if we can answer that question. A map's scale is the ratio that relates distances. This is important because we want to know how far things are from where we are. So we might want to be able to get from one place to another, like we might want to be able to get from Pasadena to Encino, or we might want to be able to get from the LA International Airport up to the Van Nuys Airport. Another reason that map scale is important is it helps us know how much space these geologic features take up. So we might want to know how big is this area of sedimentary rock, or how big is the igneous rock underneath the ground? Is it big enough and sturdy enough for us to build a city on? It also can tell us how big resources are or how far apart they are, right? If I had a little resource here in San Jose and a resource in San Francisco, then I would be able to say, oh, I can gather those resources, but I'll have to have trucks and trains and boats to ship them back and forth to each other. Okay, that was it for today. Good job, and roar Wildcats!